And here's the video homework help for problem 3.4. I especially want to remind you to look at the comments in the written homework hints on Blackboard. I won't repeat those, but if you combine those with what I say now, you'll have a lot of help. In part A, if you remember going back to 2.33, the formulas corresponding to the precession of a magnetic moment around the z-axis. By the way, magnetic moment will often just say spin or magnetic moment, interchangeably because they're parallel to each other. You remember that what we're doing for a proton, with gamma positive, we will precess clockwise, looking back around it, back along the z-axis, or what would be left-handed if you thought of a screw in the positive z direction, a left-handed screw. And when you look at the formulas, it's neat to check it. Suppose I started out in the x direction, so I only have this component and that component. Those would be 0. You can see the formula, how it works. At t equals 0, it's only along that direction. But as t goes positive, this becomes a little smaller, and this becomes bigger with a minus sign going in the opposite direction to y, and sure enough, that's clockwise precession. Now, the first thing you're going to do is you're going to adapt this, and you're going to replace omega 0 t by a phi, such that the d phi dt is minus the frequency. This came about because back in chapter 2, the omega was constant. And so that was easy. You just had phi as a minus omega 0 t, plus a constant. And now I want to do another thing. I want to define phi to be the negative of the usual cylindrical coordinate phi, so that you see the phi will then grow positively when I'm going clockwise. Well, not only that minus sign, then remember that then d phi dt, most importantly, the omega here is omega 1 in the rotating reference frame, and that depends upon time. And why does it depend upon time? Because you're going to turn this on and off and rotate that spin. So phi is not just equal to a constant, it's an integral over some function of time. And so I'll leave it like this, but I'll go from 0 to t because I want it to start out at a 0 angle at time t equals 0. Starting off, say, pointing along x, say. You can easily check this. This just gives you the old result. And the other thing to do is I can just take this answer and just relabel it and get what I want here. That is, draw the picture carefully so that the y prime is now, in the same direction as the z was there. I'm going to precess around clockwise around y prime, and make sure I draw my right-handed coordinate carefully. And this all corresponded to, I imagine, mu was along z initially. And all I do then is I'll take this z and replace it by y prime, that x and replace it by z prime. Z prime and z are the same. Y replaced by x prime. I say that here. And finally, I'm going to start out in the z direction initially, so that all the other components are 0. And you'll get, answers. You can check some of them against the written homework hints. Take that answer and go to part B. In part B, I'm going to take that answer and plug it into both sides here and see if they're equal. To start with here, my mu prime then going down as mu x prime, x hat prime, plus mu y prime, y hat prime, plus mu z prime, z hat prime, and then I'll take the cross product with y hat prime, so the y hat prime won't contribute. And then you're going to look at the corresponding x hat prime or x prime, y prime, z prime coordinates on the left-hand side. Look at both, look at x prime components on both sides. Do they match? Do the y prime components match? Do the z prime components match? And you'll see that they do. The only thing I got to remind you is when you're taking this derivative, now it's just the derivative of those components that you had from part A. You know, the x hat prime is constant in that rotating reference frame. And remember, when you're taking the derivative, you're going to take the derivative of like sines and cosines. You take the derivative of sine phi, you know you get cosine phi times the derivative of phi, and that's omega 1 from what we were saying in part A. And, you know, you'll check that everything works out okay. In fact, you know, one of the equations that you'll get is this d mu x prime dt equals omega 1 mu cosine phi. And with this thing here in part C is what I'm going to take the second derivative. I'm going to take another derivative of this, because then I'm going to get an equation involving the second derivative. And you remember in chapter 2, all we got was d second mu x prime dt squared is just equal to minus omega squared mu x prime. It was a harmonic oscillator thing. Now, because omega 1 here has itself a, it depends upon time, it has a non-zero derivative. And so I'm going to get another term, and when I take the time derivative of this to get my second derivative, I'm going to get an extra term from here that I didn't get in chapter 2. And that ends up then giving me an extra term proportional d omega 1 dt, as well as the, you know, the omega 1 squared. And I gave you an example in the written homework so that you can check it against that. The second order harmonic oscillator equations uncoupled, you know, from in chapter 2, are changed now to include first order terms which are coupled. You know, the mu x prime second derivative equation will have a mu z prime in it, and vice versa.